Today we are going to talk about the water holding capacity of the soil. The water holding capacity or the porosity of the soil helps to determine the type of crop to grow. It gives information about the soil's ability to store water and also enhances movement of nutrients to plants when available. Therefore, as a farmer, you need to know much about the water holding capacity of your soil. Now, in this experiment, we are going to talk about the water holding capacity of the soils. So, it's simply the aim of this experiment is to determine the water holding capacity of the three main types of soils. That is sandy soil, loamy soil, and then clay soil. Now we have our samples here. In this experiment, we will go through all the necessary processes to see whether which type of soil hold enough water and which type of soil has the intermediate capacity to store water and which of the soil types do not retain water at all. We don't know. I always say science is practical, science is physical. We are not waiting to send our apparatus to the lab and all those things. That is why the Smart Agro Innovations, we have tried so much to work on simple protocols to always bring out simple ideas in agriculture. Now, if a farmer wants to do something, wants to know the type of soil, he does not need to send all these things to the lab. So he or she can easily perform the necessary experiment at the lab. So in this experiment, you will determine the water holding capacity of the soil. These are the materials needed. The materials needed are cotton wool. This is cotton wool, and the main function is to sieve the soil from getting into our cylinders. Now, we also have our cylinders. These plastic bottles will serve as our cylinders. So if you can see, we have A, we have B, and we have C as the main representing our three main types of soils. So these will serve as our funnel. These will serve as our funnels. So this is our funnel, and this is ordinary water. Now the experiment. We are going to take equal value of these soil samples and then put them in the funnels, and we are going to see the end result. Yeah, so we have our funnels. So with the first procedure, we need to fix this cotton wool at the neck of the funnels. I already told you that this cotton wool will serve as a sieve to sieve the soil samples when poured in here so that it doesn't mix up with the drained water. So now the cotton wool. We have our cotton wool. Let's fixing it now here. Fix. So that is B. So possibly this is B. We have another cotton wool. And that is obviously A. So this funnel we insert it on our cylinder A. Now this is C. So we have it fixed here. Secondly, we need to pour the soil samples in here. So the procedure is the ongoing. We have our cylinder and we are going to fetch equal volumes of soils. So this is our clay soil. This is our clay soil. So we are done with this. Now we continue from this soil sample. Fetch equal volumes of the soil sample. Now back to sand. So possibly we are going to see whether they are of the same amount. I think that is it. So I will indicate the levels of the soils. Simply the level of our soils. Possibly equal volumes representing our soil samples. So once we are done, now we have our soil samples in there. I told you that this will serve as funnels. We have our cotton wool fixed at the neck nicely. Now we have our cylinders. So it's left with we are proceeding with the whole thing. We have our soil samples already fixed in the funnels inserted on the cylinder. Therefore, the practical component continues. So looking at the procedure, we need to add water, and the water must be equal quantity. At the end of the day, we are going to see which soil sample allowed water to drain through faster. So experiments continue. This is our water. This is just ordinary water in absolutely equal volume. So we move on to cylinder A. Cylinder A, funnel A. Now we don't know which soils are these. At the end of the day, we will see it. So let's go. So here we go. Another equal volume of water. We have it on cylinder B, funnel B. Here we go. I think with this, it has started draining. Let's see what happens. It's done. Now, let's look at cylinder C, funnel C. Also equal volume of water. Sorry. So now we could see that this is draining. This is also draining, and this will also start draining soon. So this is simply our setups. You can see how interesting science is. The water is draining, and this is the practical videos. It is happening live. Now you can see physically that the water is dripping bit by bit. We are going to wait for some few minutes. We will wait till 30 minutes. After 30 minutes, we will look at the results. So, stay tuned. Keep watching. The water is dripping bit by bit. The water is dripping bit by bit. This is experiment C. You can see the water dripping in there. I told you the container is serving as a cylinder. You need not to carry everything to the lab. You can perform things on your own once you stay with Smart Agro Innovations. You can see experiment A also dripping bit by bit steadily, but it's still dripping. So at the end of the day, we are going to compare the levels of water that has drained. The water in the cylinder will serve as drained water. So we will measure the quantity of the drained water and compare the whole experiment. Then we reach at a conclusion about which soil type has the highest water holding capacity. We have the three main soil types here. I believe that you are aware of these three main types of soil. Yes, here they are. At the end of the experiment, we will do our comparisons and we will rate at a conclusion to know which soil type has the highest water holding capacity. I told you that the water holding capacity helps to determine the nutrient availability, enhances the. Now, the test results. At the end of the experiment, these are the results of our setup. All the water poured in here is being drained. So practically, the water in here is known as drained water. Now we are going to compare the levels of water within the cylinders. And that is where we will reach at a conclusion that which soil was able to retain more water. So the quantity of, we pour the same amount or quantity of water in each of the setup, but at the end of the day we realize that the water that was able to drain into the cylinder, the levels are totally different. So we are going to compare the two. This was our setup A, and this is the level of water in there. This is the level of water in there. Now we move on to setup B. That is the quantity of water that has also drained. Now we move on to setup C. And this is the quantity of water that has also drained. Now we are going to compare the levels and see which water was able to retain much water here, which soil was able to retain much water, and then we do the comparison. We will also check the practical representation of the particle sizes and the pore spaces in there, simply because the porosity and the move affects the movement of water and gas exchange in the soil. The porosity of the soil, that is the pore spaces within the particle sizes, affects the movement of water and gas exchange within the soil. It also affects the transport of plant nutrients. So knowing the water holding capacity or ability of each soil type gives a good information about the pore spaces in between the soils. Now, at the end of the experiment, we realize that this is the level of our drain water. So we will mark there. Alright, so at the end of our experiment, we realized that clay soil was able to retain enough water in here. That is why the level of water here is smaller as compared to the other setups. Now, clay soil gave the least drain water, followed by loam soil and that of sandy. So it is therefore clear that this soil type is clay soil because, according to literature, according to science, clay soil has smaller pore spaces in between its particle. That is why it was able to retain enough water. So after the experiment, we can see that this is clay water, clay soil. We also have loamy soil, and that is loamy soil. And this represents sandy soil simply because the amount of drain water here is higher, because the pore spaces or the air spaces in between the particles are larger. That is why water was able to drain through faster and it couldn't retain enough water. But clay soil was able to retain enough water. That is why the level of drain water is smaller. So this is also sandy soil. Now, through science, we know that the particle sizes also helps nutrient availability of plants. How nutrient will be available to the plants, it depends on the pore spaces. Because if you look at the importance of the water holding capacity, it enhances air water movement in the soil. Above that, it also ensures the activities of microorganisms. The porosity of the soil enhances the metabolic activities of microorganisms in the soils, simply because microorganisms are also important in the growth of plants. The soil microorganisms makes nutrients like mycorrhiza available to plants through their activities. Now, let's compare the particle sizes based on literature, that is science. We realize that clay soil, this is the practical representation of the particle sizes of clay soil. So, when you compare that to sand, to loamy soil, this is the practical representation of the soil particles and their pore spaces. In sandy soil, this is also the practical representation of the particle sizes in the soil. Now let's compare. If you take that of clay soil and sandy soil, just have a look at the practical representation of the soil particle sizes. The dot dots represent the soil particles, and the spaces in between also represent the pore spaces, or how porous the soil is. Comparing the three soil types, you will see that this one, the particles are densely closer to each other as compared to loamy soil. They are not all that close and they are also not all that apart. But if you look at that of sandy soil, the particle sizes are visible to the eyes. The particle sizes are larger. The pore spaces are also larger. Let's compare them here. These are samples that we have. This is clay, this is loam, and this is sandy. You see that the particle sizes are visible to the eyes. And then also, the movement of water and nutrients in the soil depend basically in or on the particle sizes. So, at the end of the experiment, we realized that clay soil was able to retain enough water due to its particle sizes, which are densely together and did not allow the faster movement of water in between the pore spaces. That is how come it was able to retain enough water and did not allow water to penetrate through it. So few or little amount was able to drain through the clay soil. Now, with loamy soil, the practical representation of the soil particles are not densely together, neither are they far apart. Therefore, allowed water to drain through it, but in a moderate situation. So, water was able to drain though, but still it was able to retain some quantity of water that will be available for plant growth. Now with sandy soil, when you look at the soil particle sizes, they are larger and the pore spaces are also large. Therefore, water was able to drain faster. That is why higher amount of water is being collected here. This is drained water. So, one may ask, what is the importance of this water holding capacity or water retention capacity practical experiment? The main importance of it is that having knowledge about the porosity of the soil also gives you knowledge about the nutrient availability through the crop in question. For example, if you are growing a crop which requires much amount of water or which needs high amount of water, I think it is not advisable and it's clear that you can plant such type of crop in sandy soil because it needs high amount of water, and because of that, once you plant it in sandy soil, water will not be available to it, neither will nutrient be available to it. Let's use maize. Require a well-drained loam soil for its growth or for its survival, simply because it is not all that water loving. It is not also a plant that does not need enough water. So moderately drained or intermediately drained soil will be required for the growth of maize. So there are some plants which are also water loving. For example, rice. Rice is a water loving plant and it needs to be planted in soil that is able to hold enough water for its survival. So because of that, clay loam soil will be much better for the growth of rice. You can plant rice in sandy soil and expect to harvest in the next season because nutrient will not be available, air movement will also not be all that good. Though nutrient will not be available, air movement will be there, but nutrients will not be available. Water will also not be available in sandy soils for the growth of rice. So with these practical videos, it is therefore clear that having knowledge about the types of soil you are working on always helps you or help you to determine the type of crop to be grown on such soils. That is why we did this experiment for you, the farmer, to know if you are going to do something. Just fetch soil samples with this simple experiment and you'll be able to know the type of crops you are working on. With this, we realize that at the end of our experiment, clay soil, to conclude, has the highest water holding capacity, followed by loamy soil, and then sandy soil. So, this is a clear indication that clay soil has the highest water holding or retention capacity as compared to loam soil and that of sandy. So, the farmer needs to have knowledge about this. Microorganisms also need to work within certain porosity rates or certain pore spaces in between the soils. So it gives the farmer all these indications. Thank you very much for today's video. Keep subscribing, like our channel, share our channel. The Smart Agro Innovation is ready for you. Do not refuse or hesitate to comment. Let's keep the way going. Thank you very much. God bless you.